Thank you very much. It's a pleasure and an honor to be here. It's my first time in this old university, one of the oldest in Europe, I believe. So I will be asked to give an overview of Bootstrap methods in conformal field theory. This is a very large subject, and inevitably I had to make some rather drastic choices. Nevertheless, my plan is to guide you through some basics at the beginning, and then inevitably the pace will speed up. And I made, of course, a rather personal choice of material, but always trying to give pointers to what I'm omitting. So let's start with some motivations, although probably for this audience they're hardly needed. Conformal field theories are fundamental. They are really one, according to one I think powerful viewpoint, all of quantum field theory can be reduced to the study of conformal field theories, because conformal field theories are special points, signposts in the space of generic, not necessarily conformal quantum field theories. And we have increasing evidence that under certain physical conditions, the generic behavior of unitary quantum field theory is an Argy flow between two conformal fixed points, one in the UV and one in the IR. Conformal field theories have a variety of very important physical applications. From one of the most famous ones is the study of secondary phase transition in statistical mechanics, so I won't read this rather obvious list of applications. And for a more formally inclined audience, of course, conformal field theories play a fundamental role in modern string theory because they define quantum gravity in asymptotic anti-de Sitter space. So, although the name of conformal field theory has field right there in the middle, the first half of my talk, or the first 1/3 of my talk, will be trying to convince you that that's perhaps a misnomer. Conformal field theories are really not best thought in terms of the kind of fundamental fields, fundamental degrees of freedom we're used to Lagrangians with. Rather, we should really take a more abstract viewpoint. So we're going to declare that the conformal field theory is just defined abstractly by a list of local operators. So X here takes values in space-time. I'm doing this in general number of dimensions. And a set of numbers, which are the correlation functions for the complete set of local operators. And the main point, the main axiom, if you will, of conformal field theory is that this set of operators that I'm denoting with this red A letter really is an algebra. There is a product. You can take two operators at different points and you multiply them and you span them in a complete set of operators at, say, the second point with some structure constants here. And the dots here indicate the fact, to which I will come back momentarily, that really here there is an infinite sum. Even for given k, we should also consider the whole power of derivatives of the operator, but these dots in this schematic expression, we just have to keep in mind they're completely fixed kinematically from conformal invariance. And I really want to emphasize that this is not some formal asymptotic expansion. It is a true operator equation. The sum is an absolutely convergent sum. You find the first signal of divergence at the insertion of the next, say, third operator in a correlation function. The nearest operator closest to the two-dimensional expanding gives the radius of convergence. And this is the basic axioms of this abstract formulation of conformal field theory. A small caveat, we are willfully ignoring non-local observables, which do play, of course, an important role in physics. So, for example, Wilson lines in a conformal gauge theory are not captured. Obviously, they're not local operators, they are line operators. And more generally, we are ignoring all sorts of interesting observables, such as defects and boundaries. But as a first look at the problem, surely this is already very rich system. And just to make sure we're all on the same page, let me cover an elementary example. Let's take what is familiar to everybody, a free scalar field in dimension greater than 2. In 2 dimensions, scalar field is somewhat 6, so I wish to not consider it now. And so then, in that case, we really do have the luxury of writing the complete set of local operators as sum of arbitrary normal order products of derivatives of the fundamental field. And a trivial example of operator product expansion will be the one, for example, which the fundamental field itself is expanded with itself, and there is the identity operator here that gives a singularity. Here I'm actually doing the case where d is equal to 4. In more general dimension, I should have a different power here. And then there's an infinite sum where we take phi square and then arbitrary operators of this kind, where you have, in this case, instead here is 3, just have bilinears in phi with derivatives. But this is really a very special case because generically we cannot expect to write this abstract set of fields in terms of anything more fundamental. The fundamental objects are the local operator themselves, and we'll think of them abstractly as this operator algebra A. So clearly, given that we have the operator product expansion, we can apply it to an endpoint function. So we expand operator 1 and 2, we get this infinite sum, and so that reduces an endpoint function to an n-1 point function. We keep going till we reach the 1 point function. But 1 point functions, if we are doing just flat RD-dimensional space-time, are trivial because they're 0 except for the identity operator, which we normalize to 1. So by successive application of YITP, we compute all correlation functions. And so that really means that the entire content of the theory, as we have defined it, is contained in what I'm labeling, what I'm calling CFT data. So the set of quantum numbers for the local operator, which are the conformal dimension, the spin, or more generally Lorentz representation, and if we have some global symmetry that commutes with the conformal algebra, we may have additional flavor quantum numbers, and the structure constants Cijk of the operator product algebra are enough to compute an arbitrary endpoint function. But although they are enough to compute an arbitrary endpoint function, we should also be clear that if you specify this data at random, that's not going to work. This is not a consistent set of data. And crucially, of course, the structure constants must be such that the order in which operators are multiplied is immaterial, obviously, because otherwise I would get different results if I were to evaluate an endpoint function doing the product in different order. That's nonsense. So in order for this definition to make sense, it must be that the order in which I multiply operators does not matter. And we also choose, this is more than a consistent condition, is a choice. We choose to restrict attention to unitary conformal field theories, or if we are in the Euclidean setting, theories that obey reflection positivity. In statistical mechanics, there are interesting models where this is not the case, but in quantum field theory and in particle physics, unitarity, of course, is fundamental. And unitarity means, well, first of all, that from the representation theory of the conformal group, you deduce that for given Lorentz representation, the conformal dimension delta is bounded from below as a function of L. And moreover, we can always choose a real basis of operators such that the structure constants are real. And here is my second small caveat, you see it's in a slightly smaller font. By formulating the theory in this way, I'm choosing to ignore non-trivial geometries. In non-trivial geometry, it could be that the 1 point function of non-trivial operators is non-zero, and that will inevitably lead to additional constraints on the CFT data. This is familiar in 2 dimensions, where these are the constraints of modular invariance, but in higher dimensions, analogous constraints are much harder to analyze because they relate local observables to non-local observables. If you think about it for a minute, there's this coincidence in 2 dimensions. Slicing the torus partition function into different ways gives you, in both cases, a state space can be described in terms of local operators, but that's not the case in higher dimensions. And so these kind of constraints have not been incorporated into the Bootstrap program in higher dimensions so far. But nevertheless, we will see that we'll get very far even ignoring these kind of constraints, which, however, are expected to give us additional restrictions. Okay, so the Bootstrap program is an ancient idea. It dates back to some pioneering papers by Ferrara, Grill, and Polyakov in the mid-70s. And the idea is that this algebraic system, so we are basically recasting conformal field theories as algebraic systems. So we have this data, the CFT data, and they must be associative. And so, at least in spirit, this is not that different from describing a Lie algebra in terms of a set of generators and structure constants, and requiring that the system makes sense, of course, leads to a famous, beautiful classification of Lie algebras, at least if you impose that they're finite dimensional, they're semi-simple, etc. So obviously there would be analogous type of restrictions we may want to impose on CFTs, but nevertheless, at least we have the moral hope of a classification program. And indeed, this has been accomplished to a large extent, although there are still many open questions, in 2 dimensions. So in 2 dimensions, the conformal algebra is infinite dimensional. It's the algebra is the symmetry of arbitrary holomorphic parameterizations. And then, using this infinite dimensional algebra, we can recast, in some favorable cases, the infinite set of equations as a finite dimensional Bootstrap problem. And then that can be solved in some cases, and these are precisely by definition, more or less, the cases that lead to so-called rational conformal field theories, where the Bootstrap problem is finite dimensional. And so we have then a partial classification of theories. For example, theories have central charge more than 1 that are unitary, are completely classified. But nevertheless, it's also the case that many 2D theories are not rational in this sense, that the Bootstrap problem is not finite dimensional. Then the story is much less clear, and there's still a lot to be learned. In general dimensions, progress really has sped up since 2008, and that will be the focus of my talk. So we need to develop a few more technical tools to proceed. So I will start with this absolutely simplest case. We take the 4-point function of 4 identical Lorentz scalar operators. And then we do the operator problem expansion operator at position 1 and position 2, and operator at position 3 and position 4. So this, using the conformal algebra, we can organize operators in conformal families. So what is a conformal family? Is the highest way state, or in physics language, the lowest way state, is the so-called conformal primary operator, which commutes with the special conformal generator. Special conformal generators have the role of lowering operators, so you cannot lower the dimension further. And then, starting from this primary operator, we build the whole representation by acting with momenta, with derivatives. And so clearly, given that we have conformal symmetry, we can restrict the sum to the primaries rather than to the whole tower of descendants. We just restrict to the irreducible piece, if you will, and then let kinematics compute for us the contribution to the sum of the descendants. So this is written in terms of some differential operator, which are functions of the difference of position between 1 and 2, and the difference position between 3 and 4, and some derivative at 2, acting on the 2-point function of the primary operators. If in principle here, I really should have a double sum, because operator at position 1 and 2 fuse into some operator O, and operator at position 3 and 4 fuse in some operator O prime, but famously, 2-point function of 2 primary operators can be orthogonalized, and so the double sum reduces to a single sum, and this is this first line. In the second line, somewhat schematically, I have performed the action of these differential operators and written the contribution to this double OP expansion of the entire conformal family built on operator O into this function abstract function G, U, and V, which is the so-called conformal block, which by definition is just what I just said. It encodes the contribution of the infinite power of descendants of the primary operator O to the double OP. And the good news is that this function is completely fixed kinematically, at least in principle. If you want to have to get explicit expressions, you have to work a little harder. Explicit expressions are known. They are certain combinations of geometric functions in even dimensions. But even in odd dimension, there are very efficient algorithms to approximate them by recursion relations or various rational approximations. So at least from a practical viewpoint, these functions are completely known. And what is not known, on the other hand, is the particular quantum numbers that enter in the sum. We don't know a priori which particular set of operators contribute to the sum. And also, we don't know the structure constants. So, as I was emphasizing earlier, performing the OP in different orders must give the same result. But if I have, like here, identical operators, clearly the kind of operators that appear in multiplying these two operators are the same as the one that appear multiplying the first operator and the third, because the operators are identical. And so really, what crossing does is simply a reshuffling of the coordinates. We are, for example, exchanging position 1 with position 3, and then we must get the same result. And then you see that what that essentially does is exchanges these conformal cross ratios U and V. Okay, so this I had in the equation, but I didn't say in words. It is also considered a conformal symmetry, which I've already utilized, the fact that a priori we have functions with 4 coordinates, but they are, in fact, truly captured by some trivial prefactor, and then these famous conformal invariant cross ratios that are invariant under conformal transformations. And what crossing does is essentially exchange U and V up to some also trivial reshuffling of the prefactors. And so we get a sum rule of the following form. By performing the OP in the order I had in the previous slide, we get this prefactor, this first, and with this left-hand side. And by exchanging operator 1 and 3, we get to switch U and V. And these prefactors here take into account the fact that I had these schematic prefactors, functions of explicit function of x12 and x34 that give these additional contributions. So in this sum rule, let me emphasize this again. Delta phi is the conformal dimension of the external operator, which we can assume is known. But what is not known at this stage is over which set of quantum numbers the sum runs. So these are the operator O that appear in the operator product expansion of phi with itself, and the structure constants. So this was just an example, the simplest possible example, external scalars. But in principle, it's clear that if you want to impose a full set of algebraic constraints, you now have to repeat this analysis for all possible 4-point functions, where these phi A, phi J, phi K, phi L have all possible quantum numbers allowed by symmetries. And so, in particular, they need not be Lorentz scalars. Now, in practice, this is not so easy. In principle, everything is fixed by symmetry and up to these undetermined dynamical coefficients. And the conformal blocks, for example, are in principle calculable for any choice of external quantum numbers. But this is easier said than done. And there is an enormous amount, now there's a growing industry of actually evaluating the conformal blocks for external operators with spin. And the problem has not been completely solved yet, but I have no doubts that in the next few years we will get a complete solution of this entirely, if you will, algebraic combinatorial problem, determining the full set of conformal blocks in, say, 4 dimensions. In 3 dimensions, the story is a little simpler because you can dualize 2 forms, whereas in 4 dimensions they are really one of the possible contributions if you have arbitrary external spin, and so they're hard. So one thing that I want to say now, and this applies to most of the slides earlier, I'm mostly going to cite results I'm directly using. So there is an enormous amount of literature on this generalization to spinning conformal blocks, and that will fill the entire, if I were to spell names out, it will fill the entire slide. And so rather than rather than picking and choosing a couple of people, I decided not to put all the names, but it's important work and it's being done. So now that we have the sum rule, we can try to analyze it and extract non-trivial information about the theory. And here I simply want to mention something I will not talk about, but there's a beautiful story to get some partial analytic results by taking a Lorentzian OP limit. It turns out that the operators of low twist in one channel, for example, the identity is the lowest twist generally, control the asymptotics for operators of very large spin in the cross channel. And so you can get partial analytic results for anomalous dimension operator of very high spin by this method. But more generally, we must proceed numerically, and this what really triggered recent development is this famous paper from 2008 of Rattazzi, Rishkov, Stony, and Vicky, that decided to do something very pragmatic. In principle, we have this infinite set of algebraic constraints, and it really seems very intractable. But they say, well, let's see how far we can go by just choosing, for example, even the simplest possible thing, a single 4-point function, or in more recent years, people have considered a system of them, a handful of them. And then we make a further simplifying assumption. Rather than consider, so you see the sum rule here should be clear that since this equation needs to be obeyed for every u and v, which are real numbers, this equation should be interpreted as a constraint on the quantum numbers that appear in the internal channel. It's a constraint on the kind of delta and L that can appear. It's a constraint on the structure constants. So given that this has to be true for every u and v, it's an infinite set of constraints. But what they decided to do is to truncate the set of constraints. Just consider a finite set of constraints. Well, they are constraints, so they still must be satisfied. So they lead to perhaps not the most stringent or the most optimal kind of restrictions, but they still lead to rigorous, true restrictions, must be true, necessary conditions on the space of CFT data. So here is my outline for the rest of the talk. I'm already cover points 1 and 2. And I will now switch to the heart of the first part of my talk, which is this numerical bootstrap. We will see that the bootstrap gives oracles. Oracles is something that will be able to tell us no or maybe. It's a very limited type of oracle, but it's very powerful. And then from oracles, we will graduate to prophecies, actually solving actual CFTs. And then I will switch gears and study superconformal field theories, where a sort of a whole new algebraic structure will emerge in terms of some exact results. And finally, I will cover numerical results for superconformal field theories. Where do I read the time?
Well, this is a countdown. When
Oh.
it goes down to 0, you stop. You have to stop.
Okay,
Is
but
it
it's not going. But
why not?
so let me describe you the first. Okay, great. Let me describe the first really important message for this talk: the numerical oracle devised by Rattazzi, Rishkov, Stony, and Vicky. So I had this sum rule earlier. The sum rule was written as S channel equal to T channel, and now I'm doing a very trivial manipulation of it. I'm going to bring it all to the left-hand side and set it equal to 0. So here, these were the two terms that were set, one on the left and one on the right-hand side. I've simply taken the one on the right-hand side, brought it to the left with a minus sign, and I'm redefining this combination of conformal blocks to be F of delta L, U, and V. And then I've done another trivial manipulation. I've separated out the contribution of the identity operator, which is always there. For the identity operator, the conformal block G is just 1, and so this just gives me this piece. So here the sum is over all operators which are not the identity. And then I've also done a trivial rewriting. I've written what before were the square of structure constants as some weight P. And the claim to fame of P is that because the structure constant can be chosen to be real, then P is non-negative. And also, I mentioned that earlier briefly, and let me spell this out more precisely in the case of 4 dimensions. For given spin L, the dimension is bounded from below. So for non-zero spin, it's greater or equal than N plus 2, and greater or equal than 1 for spin 0. So as I was saying earlier, we want to interpret this equation as constraining the CFT data. It looks like a complicated equation, but again, we are going to Delphi and interpelling the oracle. And we would really like to decide, we have a trial spectrum. We have a fantasy that a certain set of dimension is the one that we like, and we like to ask the oracle whether we win or we lose. So for example, that's a typical thing what we can do is decide that we want dimension to be greater or equal than some delta bar. So I want, for example, the scalar, so where L equal to 0, to be greater than 7. And the spin 2 operator greater than 18. Why not? Sorry. And then I go to the oracle, and the oracle has the ability to tell me no, perhaps in some cases, or it can be undecided, it can tell me maybe. And how does the oracle work? Well, the oracle works by looking for a functional chi, a linear function that acts on the space of 2 variable functions. And if I manage to find a linear functional that is non-negative on all these f's that obey the condition of my trial spectrum, and which is normalized to 1 on the identity, then the oracle says no. Why does it say no? Because let's act with chi in this equation. Well, the p are non-negative. This combination here, by assumption, is non-negative. So this is non-negative, but this is 1, and something non-negative plus 1 cannot be equal to 0. So if I'm in the position to identify a linear function of this kind, the oracle says no. If the oracle is unable to find a function of this kind, well, we're agnostic. Perhaps a theory with this spectrum exists, perhaps it doesn't. And the good news is that we can program this rather efficiently on a computer, looking for the optimal functional given a truncation of this infinite set of equations. In practice, what's being done, one expands this infinite set of equations as a tailored series around the crossing symmetric point. So that gives an infinite, that reduces the infinite set of equations to a finite number of linear equations. And then we look for this functional by essentially linear programming or semi-definite programming method. I'm not going to go into any details about how the numerics are actually done, but you can think of this oracle as a black box that you submit to her a trial spectrum, and the oracle will say no or maybe. And here is the first prophecy, really. This is beyond oracles, we are in the realm of prophecy. So what this gentleman did in this beautiful paper, they submitted to the oracle the following question. Let's restrict ourselves to 3 dimensions, and let's consider a 4-point function of 4 identical scalar we call sigma. And as we vary the dimension of sigma, in 3-dimension unitarity restrict the dimension of sigma to greater or equal than 1/2. As we vary the dimension of sigma, we ask ourselves which value of the first scalar that appear in the OP of sigma with itself. So we have sigma times sigma equal the identity plus some scalar epsilon. And we are making one assumption. We are making the assumption that the theory has a Z2 symmetry under which sigma is odd and epsilon is even. And so in particular, you see here that epsilon does not appear, sigma does not appear in the right-hand side, so because it's odd. And so odd times odd gives us even. So epsilon, by definition, is the first Z2 even scalar that appears in the OP of sigma with itself. And then the oracle is this beautiful plot. It says, well, this blue region, we're agnostic. Maybe theories with this spectrum exist, maybe they don't. But what we can say with certainty is that the white region above is excluded. I mean, the first time you see something, this is really mind-boggling. We're analyzing a single 4-point function numerically, and we get this incredibly powerful result where we carve out, we rule out some, you could have fantasized that there is a conformal field theory in 3 dimensions where sigma is dimension 0.58 and epsilon dimension 1.6, but no, that doesn't exist. Very strong result. But what's really spectacular, and nobody really expected this, is that this plot has a very sharp feature. It has a kink, a very sharp kink that gets sharper and sharper as you implement these constraints more and more accurately. So I want to emphasize, when the oracle says no, it's a clear-cut no, because you're using a finite set of constraints, but they're true constraints. When the oracle says maybe, well, we're not sure. It's possible that if I were to impose more and more constraints, this region would be further carved out. But anyway, it does appear, however, by looking at how the numerics are converging, that we are already basically converged, and this is already the actual boundary. And then there's a sharp kink whose position coincides with extreme precision with the known values of the critical exponent of 3-dimensional universality class for the Ising model, which are known from Monte Carlo, epsilon expansion, and a variety of other techniques. So that's a real surprise. What is surprise, what you can do further, and this was done in this paper by Kospal and Simon Zaffin a couple of years ago, you can consider a more complicated system of constraint equations where you now look at the set of these three 4-point functions, 4 sigmas, 2 sigma, and 2 epsilon, and 4 epsilon. You see, this is the complete set for this lowest dimensional scalar that is compatible with the symmetry. And then the oracle now is a lot more powerful, and it becomes a lot more powerful if you make one additional crucial assumption. You're going to impose that sigma is the only scalar operator which is relevant. The next scalar operator, which I'm calling sigma prime, has to have dimension greater or equal than 3, which is the number of space-time dimensions. That is an entirely reasonable assumption, because to tune yourself to the universality class of the Ising model, which is, say, Fegnomagnets in 3 dimensions, where you need to specify 2 numbers, the temperature and the magnetic field. And that is a restatement of the physical fact that there's only 2 relevant scalars in the universality of the 3D Ising model. One which is Z2 odd, which controls the magnetic field, and one which is Z2 even, which controls the temperature. And so we certainly know very well that the 3D Ising model has a single relevant scale, the single of each parity. And by pure thought, just imposing conformal symmetry, Z2 symmetry, and this very minimal condition, there's only one relevant scalar of each parity, the oracle says no in all the Y region, and yes in this blue region, and you see that the blue region now around the Ising model has shrunk to a tiny island, which becomes smaller and smaller as you increase the accuracy. So this is a rigorous demonstration of universality of the 3D Ising model. There's a unique conformal field theory in 3 dimensions with a relevant scalar of each parity. Spectacular result. In fact, the result is so spectacular that earlier this year, David Simons-Duffing was able to beat. So this is now a zoom up version of the previous slide, in which this is the Monte Carlo determination of the critical Ising exponents, and this tiny region is the maybe region of the oracle. So these are just for fun. this gives the most accurate determination to date of the critical correspondence to the Ising, but what's conceptually even more important, that we get rigorous error bars. The Monte Carlo and epsilon expansion results are all over the place. Different groups have different results, but these are rigorous inequalities. Okay, so let's move on. So I'm not going to be able to do just all the beautiful extensions of this work. You can very much repeat the same story with ON symmetry in various dimensions, with Fermis, etc. And again, I'm not putting explicit names here because I inevitably forget somebody, so I'd rather not cite anybody if I'm not explicitly looking at their results. But there's a whole industry that leads to essentially two types of results. On the one hand, you can apply the oracle and decide, give rigorous inequalities, yes or maybe, sorry, no or maybe. But then, if you're lucky, and it happens that your theory sits at a kink, or even better, if it sits at a shrinking island, then you get what I'm calling prophecies. And then you get high precision results for specific models. And I don't really have time to explain this, perhaps somebody can ask me later, but one can argue that whenever a bound is saturated, the sum rule has a unique solution. So in fact, you get not only results about the particular exponents that you're bounding, for example, in the two-dimensional plot earlier, we were getting results about delta sigma, delta epsilon, but in principle, if one had infinite accuracy, one would get, in fact, the complete solution of the theory, because the Bootstrap equation is expected to have a unique solution. Okay, so now I'm going to switch gears rather drastically and talk about superconformal field theories. So actually, a lot of what I said before can be repeated with somewhat more technical involved discussion for superconformal field theories. You simply put a super in front of conformal. Well, you have conformal word identities, now they become superconformal word identities. You have conformal blocks, now they become superconformal blocks. So obviously what you want to do is organize operators according to unitary representation of the superconformal algebra and resum the entire tower of superconformal descendants that gives superconformal blocks, and that's a straightforward step. However, of course, it's again, in practice, this is easier said than done because superconformal representation theory is tricky. Superconformal algebras exist in dimensions smaller or equal than 6. There are many of them. For each of them, there are many. There's a whole intricate zoo of shortening conditions. And so this gets complicated. And there's no general theory yet. So far, it's mostly a case-by-case study. For a given superalgebra, you look at this particular shortening condition, you find a variety of tricks, sometimes very ingenious, to evaluate the superconformal blocks. So again, I'm not giving the order 40 references of people who are doing all this heroic work. And I'm, however, going to tell you about one true novelty that emerges in a superconformal case. And the true novelty, as perhaps you could have expected, or if you're an optimist, you should have expected, is that when you have supersymmetry, at least when you have enough supersymmetry, solvability should be something which you want to think about. And so you cannot really hope to exactly solve the full theory, but what you can hope for, as often is the case with supersymmetry, is to find a subset of the theory which you can solve. And so that leads really to a very natural question. Is there a solvable truncation of the Bootstrap equations for superconformal field theories? And it turns out that yes, there is, for very large classes of important theories. In fact, any four-dimensional theory which has at least n equal to 2 supersymmetry, that includes, of course, n equals to 4, or in 6 dimensions, the very important case of theory with 2-0 superconformal symmetry, which are very mysterious and very elusive, they do admit a protected subsector, and rather magically, this protected subsector turns out to be isomorphic to the chiral half of a two-dimensional conformal field theory, to what is sometimes called a two-dimensional chiral algebra. Mathematicians would call it a vertex operator algebra. And in fact, there is a similar story, somewhat less powerful, but still interesting, for three-dimensional theory which have at least n equal to 4 superconformal symmetry, where you find a one-dimensional topological quantum field theory. So here is some references to the 3D case, but in the rest of the talk, I will describe the cases of n equal to 2 in 4D and 2, 0 in 6. So what's the story? Very schematic. Unfortunately, I don't really have another. So by the way, this is work that I've done with my collaborators in recent years, so the references were in the previous slide. It turns out that theories with this amount of supersymmetry in 4 and 6 dimensions admit a subsector of the operator algebra where one, first of all, restricts by hand the operators to lie on a plane. You choose the plane inside RD and parameterize it by Z and Z bar, holomorphic and anti-holomorphic coordinates on the plane. And it turns out that if you carefully choose the operators you're talking about, the endpoint function of them, which a priori would be a function of Z and Z bar, in fact, is only a function of Z. It's a meromorphic function of the Z coordinates. And the rationale for this little miracle is that this subsector is defined by passing to the cohomology of a certain nilpotent supercharge, and the only novelty with respect to more familiar cohomological constructions in supersymmetry is that now we're utilizing in a crucial way the superconformal algebra. So this supercharge is a linear combination of a Poincare and a superconformal supercharge. And you can analyze these cohomology classes and discover that the Z-bar dependence is Q-exact. And so naturally then, at least formally, you conclude that this correlation function is meromorphic. And you're familiar with at least one instance of this, the chiral ring of n equal 1 theories in 4 dimensions. It's a stronger result in that case because any x dependence is Q-bar exact, and so correlators in the chiral ring are in fact completely topological. Here we have a weaker result, but in some sense that's better news, because topological theories are much less interesting than meromorphic theories. So here we have a remnant structure which is still very powerful, is the structure of two-dimensional chiral algebras. So I really only can highlight some of the results here. Let me first describe the story in the 4D case for a generic n equal to 2 superconformal field theory. A first real surprise. By construction, we're restricting the correlation function on the plane. And so obviously we have SL2 symmetry that acts as Möbius invariance of the Z coordinate. But the true miracle that happens is that gets enhanced to Virasoro symmetry in this subsector of the theory. So the theory really has, in this particular subsector, infinite dimensional symmetry. And what you identify as the meromorphic stress tensor of this two-dimensional chiral algebra has its 4D origin into the nether current of the SU2R symmetry of the n equal to 2 theory, which happens to be part of the same multiplet as the 4-dimensional stress tensor. And you can calculate the central charge of this 2D operator by a word identity you calculated, and it turns out to be minus 12, the C anomaly, which is the coefficient in front of the Weil square term in the trace anomaly of the 4D theory. So the 2D stress tensor is more related to the 4D stress tensor because it's related to the arc symmetry current, which is part of the same multiplet, and the anomalies are related as such. Note that since the 4D theory by assumption is unitary, so C is positive, the 2D chiral algebra is necessarily non-unitary because C is negative. There's a similar story for flavored symmetries. If you have a flavored symmetry, n equal to 2 supersymmetry will require the flavor current to be part of a multiplet whose lowest component is the so-called moment map. which is a scalar of dimension 2, which is an arc symmetry triplet.